Hello, and welcome to part 2 of 6.3. So we are continuing with binomial random variables today, and then I also want to talk about geometric random variables. So first of all, in class we talked a little bit about the shape of a binomial distribution. So I just want to recap really quick. Depending on what the probability of success is, the shape changes. So if you were to graph this out in a histogram, when the probability of success is equal to 0.5, this is when the distribution of the graph of the histogram is going to be symmetric. If the probability of success is less than 0.5, so you have like a lower chance of being successful, then your graph is going to be right skewed. If it's greater than 0.5 for your probability of success, then it's going to be left skewed, so it's the opposite. And then the last thing that we haven't talked about yet is if your n times p, which is the formula for the mean of the distribution of your binomial random variable, is greater than or equal to 10, and if n times 1 minus p is also greater than or equal to 10, then it's actually approximately normal. So that's kind of cool. Which basically is talking about if your n, the number of trials that you have, is large enough, no matter what p is, if n is large enough, we can kind of get an approximately normal distribution here, which is nice because normal distributions are a lot easier to find probabilities of. And this is mostly used in more in real life because our graphing calculators technology can only do so much. So when we use Binom PDF, when we use Binom CDF, those probabilities, when the numbers are really big for n, it's harder for technology to calculate because, there's just a lot more numbers to work with. And so with the normal distribution, we can just use table A, normal CDF, easier to calculate probabilities that way, and to approximate. So when both of these rules are fulfilled, the n times p is greater than 10 and the n times 1 minus p is greater than 10. This is actually called the large counts condition because it's basically saying you have big numbers, this is good. Or large sample sizes, that's also good. So when that happens, we can use approximate normal distributions to calculate probabilities. And so when we use normal curves to find our probabilities, the mean is just the mean of the binomial random variable, which we can find by doing n times p. And then the standard deviation is just the standard deviation of the binomial random variable, which is the square root of n times p times 1 minus p. And so once you have this set up with the mean and the standard deviation, then you would find everything else the normal way. Find your z-score, use table A or the normal CDF function in your calculator to calculate the probabilities.
All right, outfit change and classroom change. So I had to film this video in 2 separate days because it's been a mess. But here we go, continuing on. So I wanted to do an example with the normal approximation. So doing a binomial probability problem using the normal curve. So in this example, we have a survey of 506 teenagers aged 14 to 18. Subjects were asked a variety of questions about their personal finance. So one question just asked if the teens had a debit card. Suppose that exactly 10% of the teams have debit cards. Let x, the random variable x, be the number of teens in a random sample of size 506 who have a debit card. So part A wants to know if you can show that the distribution of x is approximately binomial. So here, if we're trying to show something is binomial, remember we have those 4 rules of what binomial means. So it spells out bins. We want to check if it's binary, if we have independent trials, if we have a fixed number for n, and if the success probability is the same from trial to trial. So let's check those 4 things. So first, binary, success or failure. So in this case, it sounds like a success counts as a teen who has a debit card. So a failure is they don't have a debit card. So cool, got that done. So the next thing we have to check is for I, independent trials. So here we're picking people. So each of my trials is I'm going to pick a person, see if they have a debit card. So when I pick people, there's no way that I can choose a sample of people without putting the people back in, like replacement. So when we choose people, because we can't reuse the same person in our sample, then we end up with no replacement, which is dependent. If you think back to our independent and dependent events, if there's no replacement, this counts as dependent. However, to get around this, there's something called the 10% condition. So the 10% condition says that if the sample size for us is 506, is less than 10% of the population. So if you think about 10% of the population as our sample size, that would mean our population should be 10 times our sample size of 506. So 10 times 506 is 5,060. And so a population of teens, because that's who we're trying to study in this problem, a population of teenagers from 14 to 18 years old, to have a population be 5,060 or more seems reasonable, because even in the US, there's way more than 5,060 teens. So our sample size is less than 10% of the population of all teens. So if this is the case, then we can still consider these to be independent trials. The way this works, like the reasoning behind this is, like, imagine you had a giant truck full of Snickers bars. I don't know, whatever, full of Snickers bars. And so, but then there's like a few in there, just a few, less than 10% of those candy bars, of the Snicker bars in this truck are, I don't know, some other candy, Skittles, whatever, little bags of Skittles. And so if you were to like reach your hand into this truck and just pull out one thing of candy, the probability that it would be Skittles is very, very small, because there's so many Snickers in there. And then let's say you eat it, whatever you pulled out. Like, let's say you pulled out Skittles that one time. You got real lucky, got Skittles, you ate it. So there's no replacement. You can't put the Skittles back in. So the next time you draw out another piece of candy, it's no longer independent because there was no replacement. But the probability of drawing out another Skittles is still going to be very similar, because if you have like a bajillion pieces of candy in there in total, the probability is not going to change a whole lot even after you took one out and ate it. And so because of that, that small change in probability doesn't really affect the overall effect of that finding a second probability. And so this is the same reasoning here. If our sample size is less than 10% of the whole population, even if we sample these people without replacement, it doesn't change the second probability by that much. And so we kind of assume we can consider it as independent trials. So that's the reasoning behind this. The next thing we need to check for to make sure it's binomial is there has to be a set number of trials, so n. So it looks like we are drawing out a sample of 506. So each time we draw someone, that's a trial. So our sample size n is 506. And then lastly, the probability of success has to be the same for each trial, which we said it was, because we have independent trials, or pretty much independent trials, and so our probability of success for each trial would be that 10%. So, okay, so we've checked all the conditions for this situation to be binomial. Did it. Part B, check the conditions for using a normal approximation in this setting. So we were saying for a normal approximation, we have to check the large counts condition, which is that n times p has to be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10. So just plugging in my numbers here, n for us was 506, p was 0.10. When I multiply that together, I get 50.6. And so this is obviously a number that's greater than or equal to 10. And then I also need to do the same thing for 1 minus p. 1 minus p is 0.90. So when I multiply that out, I end up with 455.4, which is greater than 10. Cool. Okay, so both of these check off for our large counts condition, so we are allowed to use normal approximation for this problem. Okay, so part C, use a normal distribution to estimate the probability that 40 or fewer teens in the sample have debit cards. So setting up my normal curve. So our mean, remember the mean of a binomial distribution is n times p. So we did that earlier, n times p is 50.6. Our standard deviation is then going to be n times p times 1 minus p, square root the whole thing. So 50 times 0.10 times 0.90, and square rooting the whole thing gives us about 6.75. And then doing my shading for the picture, we want to find the probability that 40 or fewer teens in the sample have debit cards. So 40 would be a number smaller than 50.6, going to be on the left. And we're going to be shading to the left because we're asking about or fewer. Remember, whether we have like less than 40 or fewer, like less than 40 or less than or equal to 40, the area is still the same. So just keep that in mind. Just a little reminder. So now that we have everything drawn out, set up, and labeled, we can find our z-scores. So the z-score is going to be 40 minus our mean of 50.6 divided by the standard deviation of 6.75. And when I do that, I end up with negative 1.57. And using my normal CDF, I'm shading from the lower of like negative 100,000 or whatever, which is the same thing here. And then my upper would be 40. The mean was 50.6 and a standard deviation of 6.75. Paste. Remember, you can also do this with your z-score. So if you did like the negative 100,000, comma, z-score of negative 1.57, comma, 0, comma, 1. So remember, if you're using a z-score in your normal CDF, the mean and the standard deviation are always 0 and 1, respectively. Okay, so we get a probability of 0.0582 if we round. So in words, there is a 5.82% chance that 40 or fewer teens in a sample of 506 will have a debit card. And that's it. So this problem we did using a normal curve. This also would have worked here if we had used binom CDF here, because we are adding numbers from 0 all the way up to 40, because it asked for 40 or fewer. So if we did binom CDF of n of 506, p of 0.10, and our x value of 40, you would have gotten 0.06, 0.06 something. So it's about a 6% chance. So you can kind of see, like, for us, we got almost 6% chance. And if you were doing binom CDF using the binomial probabilities, it would have been similar. And this is why we call this a normal approximation. Versus the binomial, because the binomial is going to be more accurate just because it's like the actual way to calculate binomial probabilities. But again, normal approximation is better when you have just like larger sample sizes. So dealing with like more than a sample size of 506, because 506 is not that big of a sample size. And so that's why there's a little bit of a difference here. But this is how it works. All right, so the last thing I want to talk about in this section is the geometric random variables. So geometric is different than binomial because in geometric, we are counting the number of trials until a success occurs. So our random variable x stands for the trial number where the first success occurs, which means you're failing a bunch of times first, and then the trial number where you actually get a success, it counts as a geometric random variable. The other rules for geometric still is similar. You have to have independent trials, the same probability of success for each trial because of the independent trials. The only thing is there's no n. So there's no fixed number of trials because it's like basically we're going to keep trying until we get a success. So technically you could fail for forever and then finally get a success after, I don't know, whenever. So there's no fixed n. So to find the probability of a geometric random variable, the formula to me is very intuitive. So here we're going to say we're looking for the probability that the random variable x equals k. So here this means that we are trying to get a success on the kth try. That means before the kth try, all of them have to be failures. So if you look at the formula for the probability, 1 minus p, remember p is the probability of success, so 1 minus p would be the probability of failure, raised to the k minus 1 power. So let's say k was 5. That means on the 5th try, that's where we wanted a success. So the first 4 tries is where you want failures. So if you have a success on the 5th try, 4 failures in front of it would be your probability of failure raised to the 4th power. Then on the 5th try, you want a success, so times p at the end. So very intuitive to hear, like, how many failures do you want? And then finally a success. And just like a binomial variable, we can still calculate the mean and the standard deviation of a geometric random variable as well. The formula for it looks like this. So keep in mind, there's no n in a geometric random variable, so all the formulas don't have n in it. It'll be 1 over p for the mean, and the square root of 1 minus p over p squared, giant square root around that, for the standard deviation. And so let's do an example together. Let's say SpongeBob has a probability of 2% of catching a jellyfish each time he tries at jellyfish fields. We can assume that each of SpongeBob's tries are independent. So right there, they're telling us we got independent trials. What is the probability that he doesn't catch a jellyfish until the 4th try? Which means in order for this to happen, we have to fail the first time, fail the second time, fail the third time, and then succeed on the 4th try. So if he has a 2% chance of catching a jellyfish, then our success would be catching this jellyfish. The p, probability of success, would be 0.02, which means the probability of failure is 98% or 0.98. So for the probability, we are looking at the 4th try, so x equals 4. That means 1 minus 0.02, or the probability of failure, raised to the 3rd power, because 4 minus 1, and then times our probability of success of 0.02. When we do that, we get a 1.88% chance of catching a jellyfish on the 4th try. Okay, and these probabilities, again, because our calculator can do so much, we can do this in the calculator as well. So if we pull up our calculator, the menu is going to be the same place where Binom PDF, Binom CDF is. So if you go into second vars, I'm going to scroll up again because scrolling down takes forever. Binom PDF CDF is up here. We're looking for Geomet PDF CDF. So if I do Geomet PDF, because we are looking for just x equals 4, we're not trying to add anything together, so just the PDF version. It'll just ask for p, which for us was 0.02. The x value for us, we wanted it on the 4th try for a success. And again, if you don't have the updated version, you'll just need to type in p and then the x value separated by commas. So when I paste, you should have something that looks like this as what you're typing in, and then hit enter. So we get our probability that we found, the 1.88%. Okay, part B, what is the probability that SpongeBob takes fewer than 4 tries before catching a jellyfish? So fewer than 4 tries means that we are looking for x is less than 4. And here, unlike the binomial random variable, we can't actually have like 0 as an x value. Because if you think about it, we're saying x stands for when you get a success. So x equals 0 means, oh geez, so sorry. Not going to edit this out, too lazy. Okay. X equals 0 would mean you get a success on the 0th try, and like, what the heck, how does that even make sense? So in a geometric random variable, it cannot be 0. That's a nonsensical thing. So the smallest number you can have for x would be 1, getting a success on the 1st try. Cool, you did great. So here, if we're looking for the probability that x is less than 4, we're pretty much adding up x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. And we're doing less than 4, so we're not including 4. So we can just find each of these geometric PDF probabilities separately, add them together, or we do the CDF version to have our calculator add everything up for us. So second vars, I want geometric CDF so that it's cumulative and adds everything together for us. So our probability of success is 0.02. The x value, so here we want our calculator to add up from 1 until 3. So I'm going to type in 3 here. Paste. And there we go. So 5.88% chance that SpongeBob takes fewer than 4 tries to catch a jellyfish. All right. Part C, what is the probability that SpongeBob takes at least 4 tries to catch a jellyfish? So here, at least 4 means we're looking for the probability that x is greater than or equal to 4. Okay, so one thing about this is, like, obviously greater than or equal to 4 means we're adding up the probability for 4 to 5 and the probabilities for 6, 7, 8, and technically this could go on forever, because what if SpongeBob was just really bad at jellyfishing and he just kept failing? So there's no like end point for this. So you can't actually just keep adding them together. What you would have to do is actually 1 minus the probability that x is less than or equal to, or less than 4. So what we want is 4 and above. So what we don't want is anything less than 4. So like 3, 2, 1. And so if I use the calculator to find the probability that x is less than 4, which is what we just did in part B, we can just take the probability of that, subtract it from 1, and that'll give me all the numbers that I actually want, the numbers that are 4 or greater. So when I do that, I get 0.9412. So 94.12% chance that it takes SpongeBob at least 4 tries to catch a jellyfish. Okay, last part. Patrick Star, whose inner machinations of his mind are an enigma, wants to know how many tries SpongeBob must attempt before expecting a catch. So here, this is like what SpongeBob is expecting. So if you remember, expecting sounds like expected value, which is also another name for mean. So here we're really just being asked about the mean. What is the mean number of tries that SpongeBob has to make until he gets a success, before he gets a jellyfish? So to find that, the mean is just 1 over p. So our probability of success was 0.02. So 1 divided by 0.02 is 50. So that means, like, as an interpretation, on average, SpongeBob would expect to try 50 times, 50 trials before a success of catching a jellyfish. There we go. All right, that's it for this section, for this chapter, actually. So thanks for watching. Bye.